All right, so my pleasure to introduce Mautner from UCR. Will talk to us about perverse sheaves on symmetric products of C2.
Thanks very much for the invitation and for showing up after classes are finished. So I'll tell you about some joint work with Tom Braden. I'll start by giving some background, so some motivation for this work, which comes from some representation theory you can see in the geometry of the nilpotent cone, particularly this modular Springer theory story that I'll describe. Then the idea will be to take that picture and find an analog in the geometry of the SN-C2, so this n-fold symmetric product of C2. And the Hilbert scheme will play a role there. And then I'll finish by describing our results, which include a kind of modular Springer theory for this space and an algebraic description of the category of perverse sheaves on this space. So, so first, the Springer theory and the notebook. So consider G to be GLN. So this is just n by n matrices, which I'll take to be over the complex numbers, and consider the subvariety, the notebook cone. Of all notebook matrices. So matrices, in particular, there's n power 0. This is the space is, so it's a singular space. It comes with a natural GLN action. You can consider the conjugation action for the set of notebook matrices. And under this action, the space, well, you can split it into the orbits for this action, and every orbit, or nilpotent matrix up to conjugation, is determined by its Jordan canonical form. So the size of the Jordan blocks, because it's nilpotent, that's all you get. So you have this stratification of the nilpotent cone by labeled by partitions of n. So this is a nice stratification. Events. And the closure relation on these orbits is given by O lambda is contained in O mu bar, even only if lambda is less than or equal to mu in the dominance order. So for example, for n equals 4, 4, 3, 1, 2, 2, 2, 1, 1, 1, 1. Of course, it's not always the linear order, but in this case, it is. It's always symmetric with respect to taking the transpose. So it's nice partial order. An amazing property of this space is that it has a beautiful resolution of the Springer resolution. So the Springer resolution is defined n tilde defined as the set of space of pairs x comma vi. So here this is a nilpotent matrix and a full flag inside of CF. So it's a sequence of nested sequence of vector spaces of each dimension, such that we take the subspace VI and act by X on it, that we're contained inside of VI again. We look at all flags preserved by the action of our nilpotent. Forgetting the flag gives us a projection to the nilpotent cone. Some useful facts that until they can be identified with the cotangent bundle in the space of all flags. So in particular, this is smooth and algebraic symplectic. So we have this, it's also the projection pi is also generically 1-to-1. So because the total space here and tilde is symplectic and it's a resolution, we call this a symplectic resolution. Resolution of singularities. And we say that the n is a symplectic singularity. This map in particular, and in fact any symplectic resolution is semi-small. Which can be stated as saying that for any x in O lambda, the dimension of the fiber, the dimension is a complex variety, the dimension of the fiber x is less than or equal to, in this case, equal to 1/2 the codimension of O lambda in X. So it says that as the strata get smaller, the fibers don't grow too fast. So for example, if you take like CN and blow it at a point, then this will not.
So it's still 1-to-1 over the one step away from generic. That imply that, or
So it's 1-to-1 on the generic stratum, and then it's not for the others. And so we'll see it. I'll give an example.
okay, yeah, finite. Never mind.
So for example, n equals to 3. So for lambda 3, then we can here which will a generic 2x2 nilpotent matrix looks like that, and the fiber, well, there's a unique flag fixed by this matrix, the standard flag. Right, it's just a point. If you take 2-1, this corresponds to looking at the matrix of 0-1-0-0, and here the fiber turns out to be like 2 P1s joined together at a point. P1. You want to do together.
Is it VI -1, the resolution, or just VI?
So it's enough to us that VI is contained, X of VI is
There's no
contained in VI.
Okay, sorry.
So it would be equivalent if we said is contained in VI -1.
Okay, so it's complex dimension and then just real codimension. What's that complex codimension?
This is
Okay. Okay.
yeah.
Okay.
Oh, so no.
Wait, what?
This is complex.
It's complex. Okay.
Sorry.
That's right.
So here, here so in this example, so the nilpotent cone is 6-dimensional.
Oh, okay. Okay.
Is 6,
I don't know.
and the orbits, as mentioned, of O21 is sorry, 4-dimensional. So the codimension is 2. We divide by 2 to get 1, which is the dimension of this fiber. And then, of course, if we take the fiber over 0, well, every flag is preserved by the action of 0, and so we get this is the whole flag variety, and the flag variety 3 dimensions, and so you're looking at a choice of a line that's 3-dimensional plus another. So you're choosing a line instead of. So you get something. This is 6-dimensional. Sorry, this is 3-dimensional. 2 plus 1. And so you get 3 is less than or equal to 6 divided by 2. Yeah. Equality. Okay. Any other questions? So so we have this space and resolution, and a kind of amazing observation of green. Yeah. Green. This is from 1955. The number of top dimensional components of a nilpotent inside of O lambda is equal to the complex dimension of the irreducible representation of Sn labeled lambda. So if you're familiar with the representation theory of Sn, for every partition, there's a natural way of constructing an irreducible representation, and we noticed that the number of components of the fiber over X lambda is equal to the dimension. And in fact, there was something more that, like, in fact, we kind of showed that you can see the whole character of V lambda in this geometry. So, so somehow this Springer resolution is encoding kind of all the representation theoretic information about the irreducible representations of Sn as you go between the different strata. So that was kind of a surprising observation that he made, and it took a little while for people to kind of figure out where these representations were coming from. So you showed that inside of this geometry, you can see traces, literally traces of the representations. So where is the actual representation? And so this, so kind of, why does this happen? The explanation is in the Springer theory. So, and the idea is that if you consider an object that contains all of these homologies in it, the Springer sheaf. So you take the Springer sheaf is the coefficients in C. You take the constant sheaf on N tilde and take a derived push forward to N. So this is some object. It's it lives in, what sort of object is it? It lives in the constructible derived category and C coefficients. And this is an object which encodes all the homology groups. All of the fibers. So it's a single object which kind of encodes all of this information in one object. So more generally, we can replace C by any field. So I'll let K be a field. Then we can consider this object. So again, the N is still kind of a complex numbers, but we're looking at now sheaves with coefficients in the field.
Sorry, can I ask a very naive question? And so the fibers of pi, which are interesting, they are labeled, they are in one-to-one with the partitions of N, or they are like you have one such fiber for each lambda, or
So for each lambda, you have an orbit,
right?
and for any point in that orbit, the fibers are isomorphic. So if you take any two points in lambda, there's you get fibers that are
the same.
the same.
Okay.
Isomorphic.
Another naive question. Is this always true that if you keep a constant sheaf and then push forward, and then you get homology fiber side of the fibers? Is
Yeah.
that special?
So for any, if you take a proper map and take this derived push forward, you push forward the constant sheaf, then the object you get includes the chromology of all of those fibers. Namely, if you take so this is some sheaf-like object on N on the base, and if you take the stalk at any point, so you restrict it to a point in the base, then you get an object whose chromology is the chromology group center. Any other questions? So you can define this object that encodes all this information, and one way of describing Springer theory from science Springer, but appeared in this form in the work of Mautner and Pearson. For anyways, characteristic 0, and like work of Juteau much more recently. So this is in the early 80s. And Juteau and it was 2014 maybe, for arbitrary K. Says that if you look at this object, the Springer sheaf, and look at its endomorphisms, then this is isomorphic to the group algebra of the symmetric. So the
I guess I too need to ask a question. Doesn't the decomposition theorem tell you that I star of that is a direct sum of shifted intersection chromology sheaves? And because it's semi-small, then perverse sheaves go to perverse sheaves, so there'd be no shifts. So it should be just a direct sum of intersection chromology sheaves.
when K
It's C,
is C, that's right.
okay, but not when K is K.
When K is a field of positive characteristic, when the decomposition theorem doesn't hold.
Yes, oh, yeah.
And if you want to play with that, you can think about the case of n equals to 2.
Oh, no, I wasn't even thinking about positive, I got it, yeah, thanks.
But yeah, so in characteristic 0, you're right, you're totally right. This is a semi-simple object. And so, yeah, you have each IC sheaf appears with multiplicity given by the dimension of the operator chromology, or the number of components. And so that that's where you see and correspondingly endomorphisms of so the group algebra breaks up as a according to the partitions.
Yeah, symmetrizers.
It's a semi-simple algebra in characteristics. But in characteristic P, it's not semi-simple. But like what does this have to do with Green's observation? Well, the point is that this tells you that actually this algebra acts on this object, the Springer sheaf, and so you get an action of the symmetric group on the Springer sheaf, and in particular you go around all the stalks of the Springer sheaf. So it tells you that you get an action. So Sn acts on the chromology of these fibers with any coefficients. You get representation there. That's kind of where one way of seeing this symmetric group action. So this okay, so the Springer sheaf, they mentioned this is a perverse sheaf. And so this is some abelian subcategory of a constructible derived category. In characteristic 0, this category is semi-simple. You have one object for each orbit, and characteristic P, it's not semi-simple anymore. And an observation is that but for any field K, the Springer sheaf is always projected in this category, in the together category of perversions. Which tells you that this category of perverse sheaves is kind of partly governed by the symmetric group. So that this category of perverse sheaves has something to do with the implementation theory of the symmetric group. And in my thesis work from long ago, I noticed to prove that in fact this category of perverse sheaves on an L1 cone is equivalent to representations of the Schur algebra, which can be described as the endomorphism algebra of V tensor n of Sn over Sn. So where V is a n-dimensional K vector space. The modules over over this algebra, over the Schur algebra, are equivalent to the category of perverse sheaves. Okay, statement. So if you haven't seen this this algebra before, it's an algebra that kind of interpolates between representation theory of the symmetric group and representation theory of GLN, or some part of the representation theory of GLN. It's equivalent to representations of GLN, polynomial representations of GLN homogeneous of degree n. Any questions while I erase?
And then in positive characteristic, just like this is, it is what it is, or is there like a so it's a characteristic 0, you're back to your this is like GLN representations.
So for in any characteristic, that's true.
Right.
That
Oh,
there's
okay,
a
sorry.
equivalence between
Okay,
representations of the Schur algebra
Okay.
and polynomial representations of degree n.
okay,
But what changes from characteristic 0 to characteristic P is that in characteristic 0, this category is also equivalent to representations of just the symmetric group.
Yeah.
Because it's a semi-simple category.
I see. Okay, yeah,
In characteristic P, this is kind of bigger than the representation theory of the symmetric group. So the symmetric group is a group algebra is a quotient of the Schur algebra.
Okay.
The representation theory of the symmetric group is a quotient of.
Okay.
So what am I trying to tell you? The talk today is I'm trying to tell you about work with grading, where we find analogs of these two theorems for n replaced by SNC2. So we consider what happens when we so we prove an analog of like the Springer theorem and an analog of this theorem.
and so back to here, so like even in positive characteristics, like the Springer sheaf is like not a big enough projective. Is that kind of
That's right.
Okay,
Yeah,
okay.
yeah. That's right.
okay?
Is there a G? Is there some double joining of big G acting? Is there a group that you want to act on them?
So here I'm not acting
There's no.
anything. I'm just going to take things that are like constructed with respect to the standard structure. And the behavior here is a bit different. And so like I'd like to say that there's some interesting subcategory here, which behaves. Well, maybe I'll get to it. So why did we think to do this? Our motivation. So we're motivated by this idea of like representational kind of philosophy. There is a representation theory of symplectic similarities. So this kind of philosophy has become so popular that there's whenever, so the nilpotent tone is kind of the prototypical example of a symplectic singularity. As we mentioned in this, like in the setting, Springer theory tells you encode some interesting representation theory. And from the category, like category O is also somehow encoded in this geometry. And people have started looking for analogs of like when you find representation theory in the notebook code, there should be some sort of analogs. This is some sort of analogous representation theory for other symplectic singularities. And so kind of this program that Tom and I have been working on is kind of trying to understand the modular representation theory, or we're finding the modular representation theory of symplectic singularities. So we've prior to this work, we had carried out this program in the for Edgar Turk varieties. And found some different other interesting algebras by setting perverse sheaves on these different things. But okay, that's not kind of today's talk. Today we'll talk about the geometry of SNC2. So here we've got X C2, right? And we consider SNX, meaning we take X to the N, so just X, Cartesian product X, and then mod out by the action of the symmetric. So points here are unlabeled points in collection, and unlabeled points in C2, where the points can collide, and remember the multiplicity. So the strata are labeled by, again, partitions. Never remember, I get the connection. Let's see the other.
Things the other way.
So let Sn minus X be the set of so we consider configurations where the points have multiplicity lambda I. So we have a point Pi and multiplicity lambda I. It's that Pi is not equal to Bj by any. So this is some locally closed subset of SNX. And so SNX is union over this lambda. X, this is a stratification. Nice stratification. Which I'll denote by S. And so note that, like the notebook cone, our strata are labeled by partitions, but the closure relation here is different. From the notebook cone case. So here, you can remember what it looked like for n equals to 4 for the open cone case. It was this linear ordering. Here, the generic strata looks like when the 4 points are distinct. So corresponding to partition 1, 1, and 1. And then maybe 2 points can collide. And so that'll be the subregular stratum corresponding to 2, 1, 1. And then two things could happen. Either these two singletons could collide, or one of the singletons could join the two bits. So we have two here, 2, 2, or 3, 1. And then the only thing that can happen is that these points merge. You see that. Well, so it looks very different. Notice that this is no longer symmetric. This is not a symmetric partition. Process. Also, in the case of the no-bone cone, the strata, it turns out, are not simply connected, but they are equivariantly simply connected. Here we don't have a group action, or at least I see an obvious group action. So the strata are not simply connected. Rather, the fundamental group of the stratum labeled by lambda is isomorphic to the normalizer in Sn of the corresponding Young subgroup modulo Sn. So here S lambda means S lambda is the subgroup of the product of S lambda 1, that's S lambda 2. And this is isomorphic to the product of S and I's, where over I, where Mi equals the number of parts of lambda of size I. So here, at 1, we have 4 parts of size 1. So that we have S4 is the fundamental group of the open stratum. Then 3, 1, 1, we have 2 parts of size 1. So we have an S2 there. We have an S2 for 2, 2 also. And then the others have 3 open groups.
How are the dimensions kind of, like if they're on the same level, like are the dimensions still like possibly very different?
No, the dimension is given by the number of parts times 2.
Okay.
Because like what is one of these strata? It's saying like all configurations of that, like those many points in the plane.
Yeah.
And so
Yeah, you're
so
subtracting
each,
2
like,
each time.
you have
Yeah.
2 degrees of freedom for each of those points.
Yeah.
Is it easy to say what the closure relation is in general?
Yeah, so the closure relation is
Okay, it's merge and
yeah, we're fine. That's it.
Break up the parts of one partition. Make it different.
Okay. So I'm gonna erase these terms, but hopefully you will remember. Erase it down.
You can write on the backboard, but you'll cover it up as soon as you move the board back down.
Yeah, maybe
So
I'll,
only do that when you're finishing.
maybe I'll quickly write in there and we'll have it there. So N bring our K. It's my bit to K. This N. And bring our K. This projector. And category for sheaves. Equivalent to modules over in
I might have a silly question. Why is this pylon not the break group?
Why pylon not the big group? So, so let's think about the case n equals to 2. So you've got, you're looking at, so you have, you know, x2 mapping to s2x. Right, so this is a twofold cover. So generically, it's a twofold cover. And so the open orbit in here is like when you have 2 points that don't collide. And so it's the this is a twofold cover of that, where you take x2 minus the diagonal. And that's simply that's simply connected. Like C2 minus the point is C2 minus the point is simply connected. Yeah.
This is C2,
Yeah, C2, not R2.
of course. Thanks.
Okay, and so now like the nilpotent cone, this SNX is also a symplectic singularity. So if I claim that, I need to tell you what the resolution is. So the resolution is the an amazing space called the Hilbert scheme. N points in X. So this is a smooth variety parametrizing ideals I in functions on X. In other words, polynomials in two variables, such that the dimension of the quotient by I is N. And turns out that this is smooth and in fact symplectic. And it has the analog of the Springer map is the Hilbert-Chow map. Called rho n. That's from Hilda and X. That's n X, where you take an ideal and map to its support. Supportable ideal. And this is again somewhat small. And a resolution. And so in an analogy to the Springer sheet, we define the Hilbert-Chow sheet to be Fn is just the pushboard along row n of the constant sheet, the IC sheet. By the dimension, which is 2. Okay. What time am I supposed to stop at?
Guess on paper 3:50, but you could push the 4. Yeah, I don't think anyone's
We
mind.
started late.
Yeah, we started late anyways. Yeah, we usually
Have to make a call at 4, so I'll get up at like 3:58.
Yeah.
Don't think I,
Oh, yeah, I'll try to not like.
just I don't want you to be insulted when I have to get up.
Sure. Okay, so, yeah. First theorem is that, so what's the endomorphism algebra of this silver tower sheet? Prove that it's isomorphic to, the Grothendieck group, or the Grothendieck ring of rep Sn. Where would be complex representations. That's a ring defined over the integers. We tensor with K.
This is a ring with the like Kronecker product,
Uh,
or
the-
sorry, or like
The tensor product on
tensor product. That's not the usual, okay, I mean, that's,
So like the in characteristic 0.
this is the product that no one understands, right?
Yeah. I mean, notice that it's a commutative ring. Right, because if you take tensor products, it doesn't matter if you take V tensor W or W tensor V, you get it's like a so it's unlike the Springer setting, this is a commutative ring. However, it's not a trivial commutative ring,
Yeah.
because when you tensor with K, like when people see the character ring, so
Yeah, just one of them.
people think, oh, that's the same thing as the center of the group object, right? But it's not. They're like they have different integral structures. They're two different lattices,
Okay.
and so they once you tensor over C, they're the same, but over K they're not. And so this has interesting representation theory, even though it's commutative. It's not so easy. Okay. So that's the first theorem. The second is that this object is projected in the category of perverse sheaves constructible with respect to our stratification. Okay, it's also actually injected as well. The same is true of the Springer sheet because it's self-dual. And then, so our second theorem, we give an explicit description of this category of perverse sheet. So this is one projective object, but we construct a whole slew of such objects. And using that collection of objects, we can prove that this category of perverse sheaves is equivalent to so we'll take category of sheaves on X to the Y to the N, where Y is a set of cardinality and take sheaves on that.
Sheaves of what? Are we,
Sheaves of-
are we still in DB?
Sheaves of complex vector spaces.
Okay.
No, we're not looking at constructive things, right? Just sheaves. So a vector space weighted by RGBN. And consider the action. So we consider that as a sheaves on SN category. So sheaves on SN is a tensor category under convolution. And so we consider this as a as a module over this tensor category, and then consider endomorphisms of this. This gives us category of endomorphisms. And the thing is, we take the K group of this tensor with K. So this, oh, and I wrote it on the
Modules.
backboard instead of the.
No, that's not the back.
No, but
Oh, you want to see the back.
no, I messed myself up because
Yeah, that's exactly, yeah,
I can't show you this at the same time. As I'm showing you
but you want modules over this
this.
tensor.
Yeah, modules.
Okay.
And the modules over the K group of the endomorphisms. And so this thing, like, so this is some complicated thing, but you notice if you forget like from sheaves to functions, then you recover the shroud. So there's a this algebra surjects onto the shroud. The surjection for this, the shroud is a quotient. Okay, but so like that looks weird. I don't, I find categorical things a little hard to rock. And so I'll give you a different description. So the so where does what is the saying? So the idea is that for any so idea of the second theorem is that for any composition lambda n, so meaning a collection of positive integers that's like n, you can take rho lambda. So you take the product of Hilbert schemes of lambda I points like x, and not to Sn by taking the, so here's a collection of ideals, and you send it to the sum of the supports of those ideals. So when lambda is just n, we get back the Hilbert-Chow map. When lambda is 1, 1, 1, 1, 1, 1, 1, this just becomes x plus x plus x plus x. So it's just x to the n, and so this map is just the symmetrization map. So we have a whole bunch of these maps at the two extremes. We have the Hilbert-Chow map, and the other extreme we have the symmetrization map. We let f lambda be the again the push forward corresponding push forward G. So the space has the same total dimension. It turns out that this is again perverse. We show that the sum of these guys is a projective generator. Of the category of perverse sheaves. And it's also an injective cogent. And so then if we want to understand, so once we have that statement, if we want to understand the category, it's enough to understand Hom between f lambda and f mu and how these Homs compose. And so continued is that for any compositions lambda mu, from f lambda to f mu can be identified with the K group of sheaves on the quotient stack Sn mod S lambda mod S mu. So here, I mean, in other words, that's S lambda equivariant sheaves on Sn mod S mu.
Here, the ordering and the composition. Seems like it really matters on this, like between them.
So
Yeah.
you mean the composition versus the
Yeah, it seems like the ordering on the compositions like really matters on like. Or does
well,
it?
so you'll get isomorphic objects.
Yeah,
if
yeah.
you change mu, like
Okay.
you permute the parts of mu.
Yeah.
And so the Hom space would be, the Hom spaces are isomorphic.
Right.
If you change the order of the parts. By doing this allows us to kind of get nicer relations, or like write down generators in those. And what is the composition? If we want to compose two Hom spaces, so we should get a map to Hom f lambda f mu. And so this was identified with the map induced by the convolution product. So there's a convolution product with sheaves on Sn mod S mu on S mu, sheaves on Sn mod S lambda mod S mu. So sheaves on Sn mod S lambda mod S mu. And so maybe if you've got lost by now, let's take n lambda mu to be equal to n. Then we're looking at sheaves on Sn mod Sn mod Sn. That's sheaves on a point mod Sn, which is the same thing as rep Sn. So we get the K group of rep Sn times with K. We've recovered. We've recovered this theorem. And Fn to Fn is the K group of rep Sn. Whereas at the other extreme, if you take lambda mu to be 1, 1, 1, 1, 1, then we're taking sheaves on Sn, sheaves on Sn, and the convolution product. So that's the so we get the group algebra. So we get this category kind of interpolates from the symmetric representations of the symmetric group to representations of the character. So
Don't worry about it.
Wow.
thanks for coming.
Yeah.
Do you have any questions before you run out?
I assumed when you told us about the structure of I1 of S in sub lambda, that it was to somehow describe all the cohomology local systems on the sheaf. Is that why you told us that? And is it involved?
So like at the end of the story, I'd like to describe.
Just need a yes or no, because I gotta go.
I'd like to describe the block structure of this category and understand which local systems belong to which blocks, like which ones
Right.
can be.
And that's where you use it.
And
The
that's where-
structure.
that's where that's.
Okay, thanks.
Thanks for coming.
Yep.
So, yeah, so I'll just conclude by saying that, we kind of prove this through generators and relations that we kind of write down. Describe generators and relations for the algebra described like this. And then check the results here. And then our generators and relations give a diagrammatic description of this algebra. If anyone's interested afterwards, I can tell you a little bit about work in progress on I'm trying to understand the block structure of this category. And I think I've used up my time, so thanks for your attention.
Any question? The Zoom
I
audience.
have a question.
Okay.
So I guess, when I see something that's done for a cotangent bundle of 5 variety and then someone put a whole scheme of points in C2, I think could it be done for any non-achievement variety? Like how specific is all of this to like exactly this setup?
I don't know. I mean, we've been playing with examples, like we've taken like the ones that seem to work.
You mentioned hypertoric.
Yeah, we did the hypertoric case. Things here like, so in the original kind of my first hope, like my first conjecture was that if you did the appropriate thing, you get a highest rate category, and this is not a highest rate category, just mentioned. And like there are too many local systems, and like you get something different. It's interesting, but it's not a highest rate category. And so maybe but like they said that like this thing has a quotient, which is the Schur algebra. So there is a subcategory which is equivalent to the representations of the Schur algebra. So it has a highest rate subcategory, and I had hoped that there was. But it's kind of the opposite one that I had expected. I guess. So I don't know. So question like, does this contain a subcategory that's the highest rate category of that algebra? I don't know. Like that was what I was expecting to find, and I'm not sure how to do that or check that. And so my like original thinking on what I was expecting has changed a bit from this example. Like we get something very interesting, which is clear. Like to me, this is clearly some like in like some sort of like categorical thickening of the Schur algebra. So there's a very interesting structure here. I should mention. I wanted to say as well that there's like this Grabmeyer's correspondence that in characteristic P, so representations of symmetric groups in characteristic P, there are these things called Young modules labeled by partitions, like Grabmeyer's and like in modular representation theory of characteristic P, there's a notion of vertices, like you can associate each Young module a vertex, and Grabmeyer's correspondence gives a like bijection between Young modules with a certain vertex and some other data, and that like you can see that geometrically from looking at these projective like the indecomposable projectives in this category. You look at the indecomposable projective whose restrictions the open set gives you the Young module, and you recover like it is the projective cover of the like thing under Grabmeyer's question. So like I think there's a lot of interesting representation theory in this geometry somehow, but I also, as far as I know, this algebra is not something I'm
Any question? Like. Can you get a read on stuff on like the geometry of the fibers? So for child, like, like for example, like the functional Hilbert scheme, I guess I'm not so familiar with like representations of that K group, so
So,
like,
so yeah, like if you have the Hilbert, like Hilbert chart, the Hilbert scheme,
yeah,
you can look at the fibers and like in the
Mhm.
in the string theory picture, you have an action of the endomorphism ring on chromology of fibers. And so you have an action
yeah,
of this representation ring. And there's a description of the chromology of the fiber. So like the chromology of the functional Hilbert scheme has a beautiful description
Mhm.
in terms of like some grading, like grading on the center of the group algebra.
Yeah.
And in fact, like,
This is Farhat-Higman thing.
sorry,
This is Farhat-Higman thing. Never mind. Okay.
so I, like, we haven't written down the details, but it looks like this action is just given by like, so like chromology classes in the fiber like has a basis that are labeled by conjugacy classes. And so how does a representation act on the conjugacy class? It acts by like the corresponding entry in the character table. And so if you reduce modulo P, then you can see like which of these like you're looking at the columns of the character table and looking at which ones become like which ones are in which isotopy components. You're looking at the columns of the character table modulo P and seeing which columns become equivalent modulo P. So there's some pretty story.
Yeah, that's wow.
I'm not sure.
Okay.
Mostly connected that was to your question.
No, that's wonderful. Yeah, that's cool.
Yeah.
Follow-up question to my first one. What about for mostly like special products and most of the points on other surfaces? This is where you use or something?
We haven't done it. I should say that so like our proof here was by describing generators and relations on the algebraic side and then checking what they figure out what they work to on the corresponded to and checking the relation. But Tom has a more like kind of idea that we could do this more intuitively using work of like Bridgeland, King Bridgeland,
Read, yeah, Bridgeland King Read.
yeah. And that like, and he started checking the details and I didn't follow what he said, but he seemed to think that like you couldn't just follow what they did in these other cases, like something in the other cases, and so it's not. Well, yeah, so we haven't done. We've done that once.
Like I had a lot of questions. I should just interest. Maybe I'll just talk to them.
How much do you think simplify when it's AK to be the context?
So you say again?
But how much do you think simplify over non-positive characteristic?
So in characteristic 0, everything's semi-simple.
Right, okay.
So you still have this description, but
Yeah.
it's a semi-simple category, and so. Oh, and I should mention that like our theorem had been observed in characteristic 0. This one theorem, this one theorem. But kind of for trivial reasons, that like everything's semi-simple, and then like, the number of objects and actions.
How easy is it to say what this, like, for an example, what is this ring with this integral form when n is 3, the k Rothenburg group of rep S3.
So in our paper, we give a like quiver description.
Okay.
Is that the sort of thing?
Yeah, that'd be fine.
But like Yeah,
I
so,
guess, I don't know. Is it, just do I have some? Maybe, I mean, this is the sort of thing that maybe I should just ask you later, because it's kind of technical, but
I can't tell you off the top of my head
Okay.
what the quicker description is.
but you have a description of the whole category, right? Like the sum space,
Yeah,
that's value generators relations.
yeah, so the
So that's
description
good.
is this, so I start to. The like a diagrammatic description of this algebra. So maybe I'll do that for the rest of you. So that you have idempotents labeled by compositions. And generators which are given by splits. And merges. Swaps. Where the relations are standard associativity. You merge and swap, that's the thing that is merging. With it. You have you merge and swap like that, and it's and then you have a sort of Mackey relation. Where you sum over all possible ways of splitting it. Thanks for your.
And so the thickest endomorphisms and then like the thickest object were,
Yeah,
which is like one part,
yeah. So if you have
that's your,
like N,
yeah,
so endomorphisms can only things that like split and then.
yeah, how can you? I'm having trouble seeing how you actually have any interesting endomorphisms of that kind. Is it like a digon? Okay,
Oh,
Things like that.
so your algorithms generate right little digons like this, and they can be. Okay, thanks.
And so, yeah, this is where rep or like the character.
Yeah.
Verification. And I guess that like. Yeah, so like these are, such guys are labeled by. Partitions, right?
Mhm.
And so these are, like, these correspond to, I guess, the young modules. Induced modules.
Awesome.
oh, let's give one more applause and then we'll say that,
Yeah.
keep the rest private.
Thanks for coming.
Yeah.